Hello, everyone. Thanks for being here. Thanks for staying until the very end. My name is Camille. I'm a software developer in the urban planning team in ESRI R&D Center in Zurich. I'm very happy to be here, a bit nervous, but happy. And today I'm going to talk about building modeling optimization using machine learning. Before diving into the topic, I would like to say just a few words about ESRI and in particular the Zurich R&D Center. So in short, at ESRI we create maps and we develop tools to visualize, manage, analyze data in those maps in an efficient way. In Zurich, the team is working on three main products that can help cities and citizens to model and plan their city. First of all, ArcGIS Urban, don't know if you heard about it. It's a web-based solution designed to improve urban planning workflows. City Engine. City Engine is a 3D modeling software application specialized in the generation of detailed, large-scale urban environments. And we also have a team working on City Engine VR experience for more immersive exploration of cities' future projects. So now, let's imagine we're urban planners and we have to redevelop a city area, like, for instance, Boston-Dorchester Avenue. We could design many different scenarios for this exact same area. Each scenario will differ from the others. Each scenario will have a different goal in terms of quantitative outcomes. For instance, one scenario could be more residential oriented and its goal could be to maximize the number of apartments in the area. Another scenario could have to address an environmental issue, Its goal could be to optimize, for instance, the window surface of all the buildings there. So the question is, how would you design these buildings in order to achieve a specific predefined scenario goal? So in order to understand the problem a bit better, we're going to scale down this whole neighborhood situation into a single building problem. So as mentioned, when an urban planner wants to redevelop a city area or a city parcel, he will aim at designing the best building depending on his goal and the urban context. These design goals can have economic, social, and environmental dimensions. For instance, an economic factor could be to minimize the cost of a construction, for instance. A social aspect could be to maximize the number of affordable apartments. Finally, an environmental example could be to maximize the number of green spaces of the building, etc., etc. We could even think that an urban planner wants to specify multiple goals per building. But urban planning is not just about specifying the goal or the performance you want your building to achieve. It's also about dealing with zoning regulations. And the zoning regulations basically answer questions like, what is it allowed to be built, where and how? For instance, a parcel could restrict the maximum building height allowed, or setback distances, or FAR, floor area ratio, or etc., etc. The list can be endless. So when you take everything into account, so on one hand, the goal, the performance you want your building to achieve, and the zoning constraints, the whole problem starts to be pretty complex. So ideally, we would have a system that can efficiently infer the optimal building design while fulfilling the zoning constraints. By optimal building design, I mean finding the building attributes that give the optimal solution. It's an optimization problem. To illustrate that, I'm going to show you in the next slides two main use cases. So the first one, my goal will be to build the building as green as possible. To do so, I will try to maximize the number of greenery spaces on my building. I will have some attributes I can vary, which are balcony width, floor height, wall width. So the goal will be to find those attributes value that give the maximum number of green spaces. No machine learning at this point. Repeat, no machine learning at this point. I will show you in the second example how I integrated machine learning in this optimization tool to make the tool faster and more efficient. In the second example, my goal will be to build the highest possible building by maximizing the building height and FAR. So yeah, the goal will be to find the optimal value of the setback distances and building height that while considering some zoning constraints. So those are pretty simple and straightforward examples, but the approach, as you will see, can be easily extended to many urban planning challenges like site selection or cost-benefit trade-offs, for instance. Okay, so let's plant some trees. All good. So here I'm going to show you a tool implemented in CD Engine, the 3D modeling software. So on the slide, you can see a CD Engine scene with a single parcel. I procedurally generated a 3D model of a building on top of this parcel. So to do so, I encoded the geometry of the building or its geometric operations in a so-called rule file. So this rule file is written in a scripted language, which is native to CD Engine. It's called CGA, just for information. So it's a nice building, but not that green. So my question was, how should I place and distribute the balconies on this building in order to have the maximum number of trees on my building? Because nowadays we can have trees on our balconies, so that's nice. So in this problem, as I said, the attributes I can vary at the balcony width, floor height, tree height, and wall width. These attributes are specified in the rule file and define the model shown here in CD Engine. So, okay, it's working perfect. So by changing these attributes here values, you modify the generated 3D model, and therefore you modify the resulted number of trees. So here I'm defining my optimization goal, which is to maximize the number of allocated spaces for greenery. And I run the tool. Cool. So while it's running, I'm just going to explain you a little bit what it's doing. So now the tool is going through many different attributes value combination and computes the resulted number of trees. Technically speaking, there is no advanced algorithm in this tool. It is exhaustively going through all the possible combinations of attributes and at the end, pick the best solution. Should be done soon. Okay, it's done. So as you can see in the report section, bottom right of the slide, the maximum number of allocated spaces for greenery is 166, and the attributes that allows to achieve this goal is balcony width 7 meters, height floor 3.5 meters, etc., etc. Have to mention something now. I speeded up the video a lot. I mean, a lot. Because the model of the building is pretty detailed and complex, and the tool has to generate a lot of different designs, so it would take too long. But we want an optimization tool, so we want it to be fast and efficient. So let's rethink the problem using machine learning. So, as a reminder, the problem is that we want to find the optimal building attributes given a parcel. So these are the inputs and outputs of the whole system. Here is the main optimization loop. So no more trees. Here we want to build the highest possible building. So we want to maximize the building height and the FAR, floor area ratio. Don't need to know what FAR means. What you can notice here is that we have a multi-objectives optimization. That gives us a more realistic building at the end. So in addition to specifying the goal, the optimization goal, we're going to consider some zoning constraints, which are the minimum setback distances, maximum building height, maximum FAR. There is a key thing here, is the FAR variable. This is a dependent variable. It means that the FAR value depends on all the other variables' value in this system. If we were solving the problem using CD Engine, the FAR value would be computed using the procedural generation engine of CD Engine. It's a lot of engines. But as I said, I want my tool to be fast and efficient. So what I did is that model this FAR variable using a neural network. So thanks to that, I now know the link between the FAR and all the other variables in this system. So thanks to that, the computation was fast and the results were good in the sense that they were close to the theoretical optimal solution. So the tool basically is that by selecting a parcel you want to redevelop, the tool will compute the optimal building attributes, here represented by this red envelope. So just a few words about the neural network architecture and the data set I used. So I collected the data set myself using a selection of Zurich parcels, trained my model using cross-validation and grid search. For your information, I used TensorFlow Python library to build the model. So the best model I got so far, we can be further improved, contains 8 hidden layers with 5 to 25 neurons each. So we have 6 inputs, which are the parcel geometry, like parcel area, parcel perimeter, etc., etc. And we have 1 output, the FAR variable. So in conclusion, I used deep learning in this project in order to speed up the computation of the FAR variable in the context of a building modeling optimization. So this project is still at the proof of concept stage, but yeah, as I said, presented here some simple example, but the approach can be easily extended to more complex situations like multi-parcel or CD block layout optimization, for instance. This topic is part of a big discussion about computer-aided design. So in our case, the goal of such a tool would be to allow urban planners, urban designers, architects to make faster and better decisions. The tool would assist them, and I insist it's assist and not replace them in their urban design workflow by suggesting solutions that go beyond what they would typically think of. Thanks for your attention.